So let's start class. We're going to discuss test number 3. Hopefully, we should finish up multinomial regression, review for the final exam, hopefully, or at least start. Please remember, course evaluations are due on December 13th in terms of the regular evaluations. Normally, these are very important, but given the particular situation we're in, it's probably not as important as it once was. Any questions about the class at all before we get going? Okay, so test number 3. So you've all seen the overall grades for the tests. I would think that the grades for 494 were relatively comparable to what we have for test number 2. Grades for 873 were probably a little bit lower overall. To be honest, I'm not for sure why that happened. In fact, undergraduates overall had a higher average median than the graduate students. In terms of the test itself, and of course I've closed out my file. I don't know why I did that. Let's see here. So the most missed problem was 1A. So a big difference between a course that's taught in a department of statistics versus, let's say, similar material that might be taught in another department, as might occur in a distributed model, is asking questions like this, where we really want you to understand what's going into the stuff to do the calculation in R or whatever software package that you have. This really is important to understand. And unfortunately, this was the most missed. I guess what I would recommend for you to do, for those of you, with respect to the final, make sure you understand what's going on underneath all this stuff. And that's what this has given us. In the end, it's not a difficult equation. I gave you the equation on the formula sheet. A lot of you, even if you, what was the most missed question, I would say about half the students who missed points were still able to put the equation out there. They were just having problems putting this stuff inside the equation itself. On 1B, the number one thing that was missed on this was the fact that many of you were doing priors equal versus proportional. And, in A, you did have equal. B was proportional. I tried here, but I do understand why you might miss that because of what you just saw in 1A. But it also gets to, the way that I introduced discriminant analysis was I said, okay, this isn't how we're going to do it at first. The way that we're doing this on first is not how we're going to end up doing it in the end. But the reason why we do it this way is because it's easier to introduce. And I think also that was a contributing factor. Now, if you didn't do priors proportional, you didn't lose many points at all. But I did need to take off some points. And your answers were a little bit different. Yes?
I just wanted to point out, I don't know if this is true for other people, but at least for me, I think some people like in their heads, for some reason I took proportional as meaning equal. But I just want to point out that might have been the case for other people. It might not be that they just didn't know. But for some reason, that's obviously not your fault, but I think just in my head, for some reason, my brain thought proportional meant equal.
Thank you for pointing that out. And I don't think I've ever thought of that before, but that does make sense to me because it's equal to what the observed proportions were.
Because I even thought, I was like, usually we don't do it this way.
Yeah.
For some reason.
Yeah. Well, if I ever teach this class again, I will make a note about that, definitely. Let's see here. Yeah, on 1C, in the end was very easy. Because, whatever you got for 1B should lead you to a one-line set of code. What often happened is many of you were trying to actually calculate by essentially using the by hand formulas in R to do these calculations. And also to complicate things, those by hand formulas that were in R that were from my own programs corresponded to if you had priors equal. So. Uh, 2A. This was, a little bit of a proof, just to understand some of the mathematics of it. Again, this is a difference between taking a course from a stat department versus taking it from another department that's more interested in just having you just do the computer stuff. The algebra is not too bad in the end. Do note for those who take Stat 475 and 875 next semester, I often give this same question in that class on a test because we talk about logistic regression much more detailed, in more detail. And 3A, I was not expecting it, but I have a feeling why it occurred. So why are four clusters a poor choice for the number of clusters? And people were saying, well, from going from 3 to 4, you have a small distance in terms of that hierarchical tree. And that distance, basically is corresponding to what you see here. The problem is that's actually from 4 to 5. So to make the decision about how many clusters to do, think about you're doing this process in a hierarchical manner. You start with n clusters, then you go to n minus 1, then n minus 2, and you keep on going up. And so then when you get to 5, the next step is to go to 4. And if you want to stop at 4, you have to look at what's happened between 4 and 5, not 3 and 4. And so that's where students were getting tripped up. And that carried forward then in the next problem too, why are 3 clusters a good choice? So why is 4 clusters a bad choice? Is because of this extremely small distance there. Why is 3 clusters a good choice? Well, relative to what we've seen before, we have a large amount of distance. Okay, any questions about the test? Okay, so right now, your current grade in Canvas. All your grades should be there. Because of limitations in Canvas, it's not necessarily organized the best. I admit that. But you should see everything for project 1, 2, 3, the quizzes and stuff like that. In there, I also have what's your current grade right now. The way I calculate that is essentially based upon what you see for the syllabus. So test 1 was 5% of your overall grade. Test 2, 20%. Test 3, 20%. Your projects and quizzes all combined are 30% of your overall grade. What we're missing is the last 25%, the final exam. Since we're missing that then, to calculate your current grade, I take this divided by 0.75. Okay? So here's just a small example. I'm not going to go through all the details here. Of course, you can always take a look on the video too if you really want to go through all the details. With these grades, a student will get 87.75, which then corresponding to syllabus will be for a graduate student B+, undergraduate student A-. So here's the current distribution of grades in our class. So of course, I like to have everyone get an A, but overall, this distribution is decent. Almost everyone's getting B's and A's. So I've already talked about the ordering of the grades in Canvas is not what I would want. I cannot control that, or at least I have not been able to figure out how to control that. Canvas also gives other stuff that I cannot remove, like something called assignments and imported assignments. Just ignore it. The key thing is to realize this. I have an Excel spreadsheet where I keep all the grades. That is what's actually calculating your grades. I just simply upload those grades to Canvas, and that's what's being displayed. Now, after final exams are graded, what I would do is upload to Canvas your final exam grade, your overall course percentage grade, and the overall letter grade. Okay? And I'll let you know when that's up there. A discussion board post will be made available. Okay. So let's finish up multinomial regression here, unless there's any questions. Okay. So the key with multinomial regression is that we have, let's say, J different groups or J different populations. Please note that there was a bad error in the notes. I actually had 2 there, and it should have been capital J. And what we like to do is now use the model to predict what is the probability being category 1, category 2, and so on. And what we saw in the set of notes right before Thanksgiving break was we had equations that one could come up with for what each of these pies would be. And so what I've done is just taken these equations, copy, paste them here, and put hats on the parameters so that we have estimates. And I've alluded to this before, all we need to do now is use the model to come up with these pi hats. And the pi hat that is the largest corresponds to our prediction for the corresponding category, for what category a particular observation would be in. That's it. So if, let's say, pi hat 1 was the largest of all the pi hats, then I would say that particular observation should be category 1. One can actually visualize what this all looks like then. So let's say we have a case where we have 3 of these categories, these populations, these groups. And it just so happens that we have these particular models. These are not estimated models. Somehow we know what the true betas are. The whole purpose is so I can visually show you what this looks like. And my corresponding code is available in multinomial modelplot.r. And this is what it looks like. So in this particular model, we only had one x. We only had one explanatory or independent variables, x. And so we put x on the x-axis. We put pi sub j on the y-axis. So for, let's say, j is equal to 1, meaning population group number 1, I can actually plot then what pi 1 would be. And this is what we get with the black line. So what this is telling me then is that from, let me get the exact value here. When, let's see, x is greater than 1.236, which is right about here. If I project up, that's not the best. When x is greater than 1.236, we can see that I'm always going to have the highest probability for this group 1. So all those observations with x greater than 1.236 would be categorized or predicted to be population group 1. And you can see something similar for population number 2, where all the lower values are population number 2. And then the middle values, the highest probability is always population number 3. And so this plot helps you visualize how you would make these predictions. So let's take a look at how to do this in R then. So this is the wheat example. Here's the actual model, or at least part of the model. Let me see if I can get, I don't think I can get the whole model on there without taking some stuff away. So the one category was healthy. Remember, we have healthy scab and sprout wheat kernels. And if I take this expression for what pi is, put it here, plug in the corresponding estimated parameter values, also the corresponding data values, this is what I get. So notice, let's see here. I take 1 over 1 plus e raised to the, here is beta, let's see, beta hat 20, beta hat 21.65. It is a hard red winter wheat kernel. This is for observation 1. Sorry, I didn't say that to begin with. And since we had to create an indicator variable for this class of kernels, soft red winter wheat was 1, hard red winter wheat was 0. That's why you see a 0 there. If I go all the way to moisture, we see that right there. There's the corresponding beta hat. So I do it for that. I also then do a similar thing for the sprout and healthy part. And again, this all comes from this equation right here. Although I only wrote that equation in terms of one explanatory variable or one independent variable. If one wanted to, one could actually program these equations into R. See on the semester, don't worry about it. It's not going to be on the final. But there it is for your reference. The easiest way to get this, though, is you can extract from the model fit, the fitted dot values, you get the corresponding pi hats. There's pi hat 1 for the first kernel, 0.85 for healthy. We can also use the predict function to do exactly the same thing where we say type equal probs. And so using $ fitted dot values, using the predict function is very similar to what you've seen before with using the LM function, using the GLM function. Again, one of the purposes of R is to use a common, let's say, language set so that what you do with one kind of model or one kind of thing that you're doing in statistics can be applied now to another one. And so that's why we see predict fitted dot values used. And so for this first observation, we can see that the largest probability is for healthy. So we would predict healthy for that. You can have R automatically do that if you replace type equal probs with type equal class for classification. And we can see for the first observation, healthy. Let's focus in on, let's try to give some intuitive sense for what's going on here. We're going to look at observation number 269 here. And this is what's kind of highlighted in a thicker dot dash or long dash, short dash kind of line. And it's just from looking at that plot, we can see that this was observed to be a healthy. What do you think the model is going to do for its prediction? Probably predict it to be healthy because we can see how extreme it is, and it's kind of all around the healthy. It's a scab. We would expect the model to predict it to be scab because it's all around the scabs. Let's see if the model actually does that. So here is 269. When I say predict, and notice I use new data equal, I just want observation 269, and look at how high that probability is for scab. Again, that should make some intuitive sense because we see how extreme this particular observation is. You would hope your model would do something like this to have such a high probability, and in fact, it does. We can also then summarize how well this model overall does in terms of these predictions. And so we go to our summarize.class function. Let me actually turn off the spell check. Sorry, I didn't do that at the very beginning. And so we can use my summarize.class function. We take the type variable out of week. That was what these observations originally were in. We put in, well, what were the predictions? And I probably didn't say that specifically before. Hold on. So I can say classify gets the results from predict, where I say type equal class. So those are our predictions. This is what we get. The correct classification rates or prediction rates are on the diagonal of that table. The overall correct rate is 72%. So is it as high as we would like it to be? No. But it does show that we are getting some, let's say, power in our prediction. From a researcher's point of view, they would, and especially if this is at more the beginning towards the research, they would say, okay, I'm getting some results here. Let's see if maybe I can make some other measurements on these kernels so that I can do better the next time. That's how typically a researcher would approach this. We can also see the lowest correct classification rate is for Sprout. Why do you think that was? Let's look at the plot. Take a look at the color for Sprout.
Because it's more like a middle ground between the two, so it kind of like takes some features from healthy and scattered.
Exactly.
It's like harder to differentiate.
Yeah, it seems like it's always kind of fallen in the middle, what we see in this plot in terms of the red lines. And so that's why the model is having a harder time to differentiate between these kinds of kernels versus the others. Scab and healthy are much more separated. Oops. Take a look at then healthy and scab. Notice only 6% are misclassified. Okay. Let's see here. So I've already talked about that essentially with the number 269. So what I showed you was the results from using resubstitution. Now, what if we use cross-validation instead? Well, if you remember with logistic regression, to do the cross-validation, we simply wrote like a function that would remove one observation at a time, estimate the model again, get the prediction. We can do exactly the same thing here. So I'll let you look through the details of this function on your own. It just kind of emulates what we've done before. So once we actually, to run this, the function is called CV2. We put in our model. We put in the data set. What will come back out to us, at least one of the components of a list here, is these estimated probabilities using cross-validation. So remember that first observation, before with resubstitution, I believe we had about estimated pi of about 0.86. Now we have 0.85. Also, what's returned is the classifications, the predictions of the groups. So the very first observation is predicted to be healthy still. And so we can put these results into summarize.class and take a look at this. Notice the overall correct classification rate is a little bit lower. We would expect that because resubstitution is typically always bias higher. It's going to give you a bigger or a larger, let's say a rosier picture of how well this model will do than a cross-validation or even some of the other methods that we've talked about in the past. And one thing that you should always do too is do like a plot of the various methods that you are using to make predictions for these, in this case, the different types of weak kernels. Unfortunately, I didn't organize this very well. In the middle, for some reason, there's where overall is. So this is a trellis plot. And we have only seen how to do this with using multinomial. But away from this, I also tried nearest neighbor classification, where I tried two different Ks that I thought were the best. I tried quadratic discriminant analysis, QDA. I tried linear discriminant analysis. And from these methods, we can see that essentially multinomial regression and quadratic discriminant analysis perform the best relative to accuracy overall. And if overall accuracy was what was most important, I would basically choose one of those two different methods. But again, the idea here, the big picture idea, is that you should always try more than one method. See how it works. Pick the method that works the best in terms of accuracy. You know, if you're more concerned about, let's say, predicting let's say the healthy kernels, we can see that multinomial does the best. That's how you approach these kinds of problems. Now, lastly here, just some really quick notes. You might be thinking, okay, we did RLC curves with logistic regression when we had two groups two populations. Can you do the same thing here with multinomial when you have perhaps more than two? And the answer is yes, but I will tell you the research is much less well defined, and so that's why I don't usually go over that, that particular topic in this class. There are many other different kinds of regression models that are like the multinomial regression model that we just saw. At least in my categorical data analysis book, I refer to these as we have a multi-category response, and there are a number of different models for it. In particular, there are models that deal with, let's say you have ordering amongst your categories. So for example here, and I do this in my book, I use this exact same data set. You might think that healthy is the most preferred type of kernel. Indeed it is. Probably the least preferred is scab, because that's essentially a diseased kernel. And then you can put sprout in the middle. So if you take into account that ordering, scab is less than sprout, is less than healthy, you can actually create a model that takes that into account. Something we talk about much more in my categorical data analysis course. I won't do it here. I just want to say this is possible. A common type of model for this is what's called a proportional odds regression model, but there are others. In this particular case, though, it doesn't help with prediction. And lastly here, there are some multinom is the first function I always go to whenever I fit one of these models that we've been talking about here. It doesn't always work the best in terms of this numerical iterative procedure, and sometimes it might not converge, and so you have to take into account you might need to try a larger number of iterations. And so that's what this note talks about a little bit there, if you're interested in exploring that further. There is another function out there from a package called VGAM that I also talk about in my categorical class, which, at least in terms of the numerical iterative procedure, is better. But there are some things that are not as good about it. And so in my categorical class, I talk about both. I at least want to put it out there that there is other ways to fit these kinds of models. Okay, any questions? Okay, let's talk about the final exam. I think we'll be able to actually finish this today. So this is a comprehensive exam. It does include multinomial regression. I think I finished writing the exam the other day. I think there's about 15 points for multinomial regression, so not much. It does not include questions, direct questions from the test number 1 material, because that's kind of background material for this course. There is a format change for this. I do this to try to help you out, and that is you won't need to use a computer. It will all be on paper. There will be printed computer output inside the test, and you will need to grab what you need from that output. So I might, for example, use both linear discriminant analysis, quadratic discriminant analysis, and and have the output in the test. And I'll say, okay, using quadratic discriminant analysis, do something. And so you'll need to figure out, okay, which function, which part of the output do I look at? Okay. You will not need a calculator for this test. So even though you won't have access, you won't be using the computer at all. You will not need to use a calculator to do any kind of calculations. Rather, for example, I might have you show me, for example, how would you calculate a principal component score? So you actually set up the equation, but you don't do the final calculation. It's closed book, closed note, closed video. Fortunately, we're the Friday of finals week at 7:30 a.m. So we'll start at 7:30 and at 9:30. The structure, yes?
I was just going to ask about in the R part, there'll be like code and output.
Yes.
Right?
Yep.
Show which code.
Both.
Which output.
Yeah. Final exam structure. Very similar problem types. Need to show your work. There will be, again, that one short answer problem set at the end. In terms of the actual material that's on the tests, in terms of why we normally do a final exam review, I would say exactly the same thing as I did for the test number 2, test 3 reviews. So please see the corresponding videos. As for the stuff that we haven't reviewed for before, it's just the multinomial regression. So what's important? Estimate and state the model. So make sure know how to do that. Make sure you get your hats on the correct things, for example. How to estimate pi and use it for predicting the groups, which we talked about today. The whole concept of cross-validation, how to choose the best method. That's the important stuff. Okay. So, I've kind of went through some stuff maybe a little bit more faster than normal today. There's one reason why. Given what has happened this semester, I decided to try to do something for the very first time in any class I've ever done. And that is, I'm going to give you 2 different options about the final exam. One, you don't need to take it. If you're satisfied with what your grade is right now, what I have listed in Canvas, that will be your final exam. That will be your overall grade for the course. Okay? The second option, take the final exam. And your grade will be calculated exactly as what's on the syllabus. I need to know what your choice is, and I have a feeling what most of your choices will be. But I also do understand that, let's say maybe you have a B right now. You might want to say, okay, maybe I can try to get an A. Maybe. So that's why I leave this other option open. But I need every single individual here to go to Canvas, and this will be available starting at 2 p.m. There will be like a little Canvas survey. And you tell me what you're going to do. Please do this. Don't put it off. Don't make me guess. Please do that. This is what what it looks like. Will you be taking the final exam? It is due December 15th at 5 p.m. Yes.
So if you do take the final exam, if you get a grade lower than what you need to keep where you're at, will that affect your grade?
It could lower your grade. So essentially, if you take the final exam, it's like just what I originally had on the syllabus. Okay. I guess when I was thinking about doing this or not, I was concerned that maybe some students might be concerned about that aspect, that indeed it could lower your grade. And the one thing that I thought of is that some students might say, okay, perhaps Chris at the end would have scaled grades in the course. And so one is that perhaps a disadvantage if not everyone is taking the final exam. I have never scaled any grades in my 30 plus years of teaching, and I have no plans of doing that again or doing it ever. I guess I always have the concept or the thought of, the grade that you get is the grade that you earn. I don't think I make my class so difficult that scaling would actually be needed. So there would have been no scaling, and there will be no scaling. You have a choice. Okay? Again, by December 15th, 5 p.m., if you know what your decision is now, just do it right after class. Okay? Submit the survey. Now, there's some of you I know who are signed up for 475, 875 in the spring, and some of you may be still considering it. Do not expect the same final exam option. I teach the course using a blended learning approach, where typically on Tuesdays, is our main class where students are expected to watch some videos before that class. I will talk about some stuff that I know that students have issues with or problems with. I also present other examples to help reinforce some aspects in those videos. That's what a normal Tuesday class will look like. Also, we'll spend more time talking about going over tests, going over projects than what we would have done in this class. The Thursday class, and by the way, it is in this room. The Thursday class is, I will come to this classroom without any prepared material at all. This will be then an opportunity for you to ask me questions and specifically to work on, let's say, projects with your, again, will be group work on projects with your group members, and I am here to answer questions that you may have. We kind of had like I guess we had one class like that earlier in the semester when I just was kind of pressed on time. And that was the best thing that I could do. Now, that's my intention for this class. But we are in unusual times right now. I am unsure if changes will be made relative to how I taught this course in the past. For example, maybe I'll have a job interview and I can't be here. Okay? Any questions?
Is the final exam in here?
Yeah. I hope the doors are open to the building. I've actually given a final. This was actually in Hardin once. Because there's one time during finals week, it ends up being like in the evening, and the doors to Hardin were locked. Some of my students, who were not, let's say, stat majors, could not get into the building because their card would not work to get them in. That was an interesting experience. Any other questions? Yes? No. Sorry. I'm sorry. You've been tested over all this material before, except for the multinomial regression stuff. So there's only one little thing that you haven't been assessed about. So yes. This is the one time when I do not share answer keys. So, I mean, that's with any time that I give a final exam, or pretty much any time, I should say. I do not share answer keys. I'm not going to distribute the test. Other questions? Yes. Yeah, thank you for bringing that up. So, the number one thing that I want to add to this class, I wanted to do it, and I was going to do it this semester, was to add something called random forest. This is probably one of the leading ways to do these kinds of predictions. And so what my original intent was to rewrite my entire discriminant analysis notes to make it much shorter. Perhaps even throw out the factor analysis notes, which in the end we had to throw out the factor analysis notes, so that I could talk about random forests. Basically, without going into all the details, you can imagine, let's say you have, two variables, x1 and x2. And let's say that you also have a response variable y that has two categories to it, let's say 0 and 1. And what you do is you build what are called classification trees. And so let's say that x1 gives you, let's say, the most power to differentiate between the 0 and the 1 categories. So let's say if x1 is, let's say, we'll say less than 3, some kind of numerical value, then you're going to go this direction on the tree, otherwise go that direction. And then maybe your next most predictive way to differentiate amongst the two different levels of y is with x2. And let's say if x2 is, let's say, less than -1, we go this way, we go that way, we predict a 0, we predict a 1. You could do a similar thing over here for x2. Maybe now it's less than 2. Predict. Okay? That's what's called a classification tree. Often people refer to these as CART, classification and regression trees. You can actually do like a regression model with this as well, where it's not, you're not predicting categories. Now, the problem with this, with CART, is it's not robust to now applying this to a new data set. And that originally, when these ideas were first developed, that was a side effect. Then people came up with the idea, okay, let's combine this with something called, or what they ended up calling random forest, where the basic idea is this. Suppose we randomly sample from our data. Let's say the same size as the original data set, but we're randomly sampling. So you could actually get the same observation in your data set twice or 3 times. We do that, we build a tree. Now, we go and do it again, build a tree. And you keep on doing this over and over again. And through that process, you can somehow, let's say, aggregate all these kinds of predictions to come up with one way to do the prediction of 0 or 1. And so the reason why it's called a random forest is because we are randomly selecting observations for every single, let's say, iteration. And it's a forest because you have more than one tree. In the end, you use a procedure called the bootstrap in statistics to do this, which I took a whole class on when I was in grad school and done a lot of stuff with the bootstrap. This is one of the top ways to do this prediction, and I wanted to add that this semester, but unfortunately, these are the consequences of what happens when your department's eliminated. Any other questions? Okay. So what's next in our class? I'll have office hours after today or after our class. On Thursday, well, I will be in the classroom here if you want to answer me questions, but I'm not going to present anything. It's more if you want to talk about studying for the final, if you end up taking the final, or if you want to talk about anything else. I will be here in the classroom. Then, for those of you who choose to take the final, it's Friday, December 19th at 7:30 a.m. If you end up choosing not to take the final or coming on Thursday, I think this is actually the last time for some of us that we'll see each other. And even for those of you who I do see again, just thank you for taking the class.